So let's say that C is an additive category. So we have a zero object, and we have a morphism between two objects, let's say A and B. And I want to understand what the kernel of that guy is. So the kernel of F, let me call it K, it's not only an object of the category, but it actually comes with a morphism to A. And it has the property that the composition with F, it's probably better to do it like this. So the composition with F of that guy is 0. So this composition here is the zero map. And it's universal in the sense that if I have any other object, K prime, and probably probably I messed up completely every arrow on every side. I'm not going to waste time looking at the video, but most probably I got a mess last time. So if I have any other guy with the same properties, namely an object of the category with a map to A such that this composition is 0, then this morphism from here to A factors through a map by K. So this is the one that exists and is unique. So that's the definition of a kernel. Okay, so this is the universal property that this K has. This K, or this I has, is a map to A that composed with F is 0, and any other map to A that composed to F is 0 factors through a map by K. So probably I defined co-kernel last time. So if you turn around every arrow, that's a definition of a co-kernel. This is not the usual definition if you don't have this thing 0 here. So if you don't have this thing 0, you cannot compare one map with a given map 0. You need to compare two different maps. So if you don't have 0, you say, well, if I have two maps, they become the same. So, okay. Anyways, so in all our categories, we're going to have 0. So that's the definition of kernel. The second thing that I certainly got wrong, because, well, not wrong, but just I chose a different sign convention, was the cone of amorphism. So if I have two complexes now, let's say I have my complex, I think C and D are. So now these are complexes. These are chain complexes, and I have my morphism F of chain complexes. So here is a morphism in chain complexes. So F is a morphism of chain complexes between C and D. And remember, when I write chain complexes, I mean chain complexes of R modules for right R modules, or it could be left R modules, or it could be just any abelian category. It doesn't matter. But it's complexes. And I have a morphism between them. And, well, the thing we did, does anyone remember the letters I've used? Because I'm kind of sure, well, I was expecting D to be the double complex, but probably I didn't use D for the double complex. Okay, so I'll probably use cone F. So what we do is we cook up a double complex. I'll try this time to use the arrows in the right, so going left. So what we'll do is I'll put, well, we get two choices. And I don't remember what I did last time. I think I put this guy in degree -1 was the last choice that we chose, and then the complex C in the first arrow, in 0th arrow. So I think that was the final choice that we chose. If no one remembers, we're going to check this in a second. But let's do this. It's Gn plus 1 maps to Dn. This is the differential of the complex D. Maps to Dn minus 1. So this is the differential of the complex D. Probably I'll avoid cluttering this anymore. This comes from before. Oh, shit. I just said that the arrows, I was going to draw them in the other direction. Dn minus 1, Dn plus 1, and the differentials go in the other direction. Let's just not write this one. And let's use this C. So in which order I want to have the arrows this time? So what I'll do is I'll take D. We know the answer, right? Because we already know that what we want is to have this guy plus C shifted by 1. So that's what we found out last time, that we wanted to be the cone of F as a graded object. I think this is what we ended up deciding, that as a graded object was going to be. We could shift this by 1. So I could have used D1 plus C, which probably I used that last time. Unless someone corrects me now, can tell me what I did last time. But either shifting of this is fine. The whole point is that this one is shifted by -1, and this one is shifted by 0. Or the difference between these two shifts is -1. So what I'll do is I'll put this guy in row 1. So I'm going to have rows probably this way. This guy I'm going to have in row 0. And in row 1, I'm going to put C shifted by -1. So C shifted by -1, remember that this meant that in the column n, I need to put Cn minus 1. So in this column, what's going to come here is going to be Cn minus 1. So here I should put a Cn minus 2. And here I should put a Cn, a Cn. Okay? And then the sum of these things is going to be my cone of F. But as a double complex, what I have is, well, Dn minus 1, Dn plus 1. I'm going to have here Cn. Notice the difference. I'm not shifting this time. Cn plus 1, Cn minus 1. Again, the differentials here are the differentials of the C complex. This continues. This continues. This continues. And this continues. And I have chain maps. So this is Fn minus 1. This is Fn. This is Fn plus 1. And this double complex, the total complex of this double complex is going to be the cone of F. So cone of F. And I'm going to fix the signs in a second so that it agrees with whatever the book uses. It's the total complex of that thing. Just write it here. Cone of F is the total complex of this double complex. Okay, so the total complex was a sum of this double complex in row P, column P and row Q, such that P plus Q has n is n. That's what I put in degree n. So the cone of F in degree n is a direct sum of things that, so this is in row 0, this is in row 1, and I want to have, well, this is in row 0 plus n, so this is in degree n, and this is in degree n, which is Cn minus 1. Okay, so now I'm drawing the arrows this direction. That's why the diagonals are more reasonable. Last time they were going in that direction. So this is in degree n, this is in degree n plus 1, and so forth. Okay? So cone f of n is Cn minus 1 plus Dn as a graded object. So we see that we get what we started looking for, which is that the cone of f as a graded object is D plus C shifted by minus 1. And the differential, now I get to choose, well, I don't get to choose the signs now. So this is not a double complex in the definition I gave last time, because I required for a double complex that this diagram anti-commutes. Okay? So, and I required that this diagram anti-commutes so that the sum of the horizontal plus the vertical differential is the differential of the total complex. That was the whole point of requiring that these things anti-commuted, so that the differential of the total complex becomes nicer and doesn't have an extra sign. But now we can, it's so simple that we can actually cook it up immediately. And let's say, what is the differential? Okay. So the differential of this guy would go from cone to cone f n minus 1. So this is the differential of the cone. So it should be a map from here to here. Well, to Cn minus 2, and here dn minus 1. And what am I going to use? Well, I'm going to use the fact that I have here f, and the fact that I have here d, and the fact that I have here d. And just to agree with the book, I'm going to put minus here and minus there. Okay? So this is f n minus 1. So I think this is the choice that the book chose, to have minuses on those and plus on d. All right. Okay, so that's the cone. And what we've seen last time, and which is the important thing of this cone, is that there's, this came from a map from C to D. And what we have is a map from D to the cone. So we have a map from C to D of complexes. This is my f that I started with. And we have a map of complexes from D to the cone of f. Which is the obvious one. Well, actually, that's a good question. Perhaps it's not the trivial one. So let's figure that out. We did it last time. The map here should be going from dn to cone of fn, which we have it there, which is cn minus 1 plus dn. And it's just the identity here. And it's 0 there. It's just that inclusion. I claim that that's a morphism of complexes. And indeed, if I apply d here to dn, I land in dn minus 1. And if I map it first and I apply d, I land in dn minus 1, and it's the identity. So this is a map of complexes as it is. And then there's also a map from the cone of f to c. But here it's not so, it's not just c, it's c shifted by 1. So let's check it. We have a map from the cone of fn, which is this guy, and I want to map it to Cn. Well, to Cn I cannot, but I can map it to Cn minus 1, which is just the projection. So if I want to map this to this, and I want it to be a map of complexes, then I better put here a minus 1. Okay, so now I want to check that whatever map I write here is a map of complexes. And I get to choose again what would be the sign of this map. If I take just the identity, so I send C plus D to C here. And I take D first. Well, D is a bad idea for this name. Shit. Let's say C plus E here to C. And I take the differential of this object. Then I take dc here. But it's minus dc here. And then if I include it, I end up in minus dc here. I can do the other way around, which is I can first map it to C, and now take the differential on this complex. And, well, this is going to have a sign depending on what was this n minus 1. Remember that the differential of this complex, I've defined it to be minus the differential in C. So it's fine. If I take C to dc, it works. To C, it works. And if I send C to minus C, it also works. Okay? So I'm going to just take the identity. Hopefully the book takes the identity and not minus the identity. But anyway, so this is a good map of complexes. All right, so we have this sequence. So people denote this sequence like this, like D to the cone of F, C, and then this guy shifted by 1, by minus 1. And we say that this is an exact triangle. And I'll get back to this later. All right, so that was last class. So let's continue with this class. I mean, what I wanted to get out of this is that, which is the important thing, is that we started with a map F, and we got this part of the sequence that is interesting. That from the target of our map, we got to a complex, and from that complex, we got to the source of our map shifted. So that's the basis of the connecting homomorphism in homology or cohomology. All right, so what else? So I guess theorem, which you all know, so probably going to go fast, is that if we have a short exact sequence of complexes, C, D, E, is exact in chains, then we get a long exact sequence. Then there exists a long exact sequence of homology groups from Hn of C to Hn of D to Hn of E. This is the hardest one to construct, to Hn minus 1 of C to Hn minus 1 of D and so forth. I'll probably just keep it there. Probably just stop there. And this comes from Hn plus 1 of E. And it continues. And this sequence is exact at every point. Let me not write this now, but many of you would know it, is that this existence of this long exact sequence, and in particular of this morphism here, is natural in the sense that if you have another short exact sequence of complexes, let's say C prime, D prime to E prime, you take the long exact sequence where every letter here gets primed, then there will be a natural map from, and if you have a map of short exact sequences from this one to the primed one, you will get a map from long exact sequences from this one to the primed one, making all of the diagrams commute. So that's naturality, and that's collection of things. Is what people call delta functors that many of you, I think, have taken the class of Eduardo last semester or during the summer, and Eduardo explained that very well in the context of algebraic geometry, at least. Or probably Eduardo did it for commutative algebra, I'm not sure. Anyways, so I'll probably write this, but let's prove that theorem. And to prove that theorem, let's use the lemma, which is the snake's lemma. So suppose we have something slightly less than that. Something like this. And we map this to something like this. So suppose that this is exact. So exact, again, means that the kernel of this map, which is all of C, is the image of this. So this map is surjective. And the kernel of this map is the image of this map. But I'm not requiring that this map is injective. There's no 0 here. Similarly here, the kernel of this map is the image of this map, which is 0. Therefore, this map is injective. the kernel of this map is the image of this map. So the kernel of this map is isomorphic to A prime, but it's not necessarily this map surjective because I don't have a 0 here. So let's suppose that we have things like this. All right, so first of all, notice that let's look at the kernel of F. So let's grab something in the kernel of F. It means that this element A, I pick an element here that goes to 0 here. Let's suppose that this diagram commutes. Let's take an element here that goes to 0 here. Well, if it goes to 0 here, in particular, it goes to 0 here. And since this diagram commutes, the image of this guy here, let's call this map I of my element here, will go to 0 here. It means that the image of this element is in the kernel of G. So there's that obvious map is I that sends the kernel of F to the kernel of G. And you can guess quickly the same phenomena. If I have something in the kernel of G here, then it would map to 0 here. Since this diagram commutes, it's going to go to 0 this way. And if it goes to 0 this way, the image of that element here is going to be in the kernel of H here. So these maps are easy to do. The same way for the co-kernels. If I get an element in the co-kernel of F, so that can be represented by an element in A prime. An element in the co-kernel of F is an element of A prime modulo the image by F. And I can just map it by this inclusion to an element in B prime. I claim that modulo the image of G, that element is well defined and it doesn't depend on the representative that I chosen for the co-kernel of F. Okay, so that's a trivial check just as we did for the kernel. So this part is also easy, that we get maps to the co-kernel of G, to the co-kernel of H. And the whole point of the lemma is that there exists some morphism here that makes this sequence exact. Okay? So that's what we want to prove, that this morphism exists and it makes the sequence exact. All right, so okay, but this sort of diagram chasing, yes.
What is it called, the snake?
Yeah. So okay, so let me draw the picture, but it goes like this. All right, so yeah. I don't know. Actually, I don't understand why people use these names. Apparently, it's stuck, but it goes like this. So here's F, here's G, here's H, and we have the kernel of H here that maps to C. We have the kernel and then 0 here. This is exact. We have the kernel of G here, and then 0 here that maps there. We have the kernel of F here, and then 0 here that maps here. And the same for the co-kernels. So there's a map from A prime to the co-kernel of F. And this map is surjective. And we have the co-kernel of G. And this map is surjective. And we have the co-kernel of H. And this map is surjective. And these arrows here are the ones that I just drew here. And these arrows here are these first arrows here. And it's called the snake because what we're constructing is an arrow this way. And it just snakes around that diagram. Okay? So we're going from that kernel here to the beginning on this side here. But anyway, so let's use diagram chasing on this diagram as it is here. What I want to construct is that map delta. So this guy here is this delta that is there. Okay? Is there any question? All right. So let's grab something in this kernel here. So let's take some element C, which is in the kernel of H. Okay? So this C is an element inside of here, which H of that guy goes to 0. But this map is surjective. So let's call this map pi. Pi inverse of C is in B. And it satisfies that H of pi of that element is 0. So let me call this guy B. Then what I know is that H of pi of B is 0. But since this diagram commutes, this is the same thing as doing first G of B and then this map. Let me call this map pi prime. And then pi prime of G of B, which is 0. So it means that G of pi of B, G of B, which is in B prime, is in the kernel of pi prime. And this is G of pi inverse of C is in the kernel of pi prime. And the kernel of pi prime, since this sequence is exact, is the image of this map, which is I prime. So it means that this G of B has to be equal to I of some element in A prime. For some A prime in A prime. So I'll just declare that the delta of C, which is the element that I started, is the class of that A prime here. So let's define delta of C to be the class of A prime modulo the image of F, which is by definition an element of the co-kernel of F. Okay, so there are a bunch of mistakes here. I cannot say equal here because this is a set and this is an element. Okay, so choose an element in this set, call it B. So it's an element in the pre-image here of Z. And now I need to check that whatever I got as a result didn't depend on that choice. So there's a choice here on this B. Once I've chosen an element in the pre-image of my original element C, I've chosen an element here. Well, I take G of that. There's nothing to choose there. I take the pre-image here again. But this map was injective, so there's only one element in the pre-image. I proved that there was one because this guy was in the kernel here. There's only one guy here. So there's no choice of this element, but there was a choice here. Okay, so what happens if I choose something different? What happens if I choose B tilde, also in the pre-image of C? Well, then what I know is that B minus B tilde, okay, is going to be in the kernel, because pi of that thing would be pi of B minus pi of B prime by B tilde, which is pi of 0. Okay? Well, sorry, which is C minus C, which is 0. Therefore, this guy here is in the kernel of pi. But if that guy is in the kernel of pi, since this sequence is exact, that guy is in the image of I. Okay, so I could have chosen this B tilde. If I choose this B tilde, then I would have gotten, instead of this A prime, which is A prime was defined to be this element that I got here. The difference of that A prime with the new one that I would have gotten by choosing B tilde would be something that comes from this A here. Okay? So the difference between delta using delta of C being A prime using B and let's say A prime tilde using B tilde would be f of A. Therefore, modulo the image of f, these two guys are the same. Okay, so I've proven that this delta does not depend on the choices that I've made. Now I need to check that what? So now we know that there exists this guy. Well, I need to check that it's a morphism, but it is. I need to check that it's really a morphism of whatever category I'm using. In particular, I need to check that it's compatible with sums and whatever it is. I leave you to do these things. Everything I've used was linear in everywhere. But then we need to check that it's exact. So we need to check exactness of this sequence. So exactness at every step here is trivial, except exactness at these points where I'm using this map delta. Okay? So I need to understand what is the kernel of this map and check that it's the image of this map. And I need to check what is the kernel of this map and check that it's the image of this map. Okay, let's try to think of doing one. I don't know if we want to do this. Okay, so let's understand here what could be the kernel of delta. So I started with this guy C, okay, which is in here, and I want to try to understand when the element that I get A prime is already in the image of F. Okay, so the kernel is all of the elements C such that delta of C is equal to 0. Delta of Z is equal to 0 if this A prime is already in the image of F. Right? So that's being 0 in that co-kernel. So I need to chase my diagram to see what happened. How could I have gotten this element already in the image of A? Okay, so I take something in the preimage here. Then I mapped it here by G. Then it was coming from an element here. And I say, but this element, A prime, let's suppose that it's coming here. It's coming from the image. Okay? Let's suppose that A prime, suppose A prime is equal to f of A for some A. But then I grab that A, and I take I of that guy. And that I of A would be the same as my B that I had here.
What exactness are you proving?
I'm proving exactness at this step. I want to check exactness in here at this point. So exactness here, well, there's no exactness claim here. Exactness here is trivial. So anything that goes to 0 here is in the image here. That's just exactness of this sequence here. Exactness at this point is trivial. Everything that goes to 0 here comes from 0 from the image here. That implies exactness at this step. But exactness at this point and at this point is not entirely trivial. So I am checking one. I'm going to leave you to check the other one. So I'm checking that the kernel of this map is the image of this map. So I'm looking when am I in the kernel. So I grabbed an element C here. And what I'm proving is that that element C, suppose delta of that C is 0. This means delta of C is A prime, which is in the image of F. So this means exists A for some A in A. So this means C is in the kernel of delta. That's the definition of being in the kernel of delta, that there exists some element A such that A prime is, which is delta of C, is equal to F of A. Okay, but now I take I of A, and that's my B that I've chosen. But then if B is I of A, it means that pi of B is 0. And then pi of I of A is pi of B, which is C, which is 0 because the sequence was exact. Okay? The composition of these two morphisms is 0. The kernel of this map was the image of this map. So I started with 0 by assuming that C was in the kernel. I am proving that it's in the image. Oh, shoot. No, I should have proven that it's in the image, that it's in the kernel of H. And indeed, yeah, should have said that first. It's not that C is 0, but that is in the kernel of G, is what I want to prove. And the thing is that here, this I of A is not B, but is something that when I apply G, it's the same as B. So here I couldn't have claimed this. What I should have claimed is that G of that guy is equal to G of B. And from there, you're going to get that C is coming from an element that is in the kernel of this map G. Okay, so this needs to be continued so that you prove exactness in the other spot, which I'm not going to do. And it needs to be continued in two different ways too, well, in three different ways. So one is easy, which is, let's do this in a different color so we can stop soon. If this sequence is also exact here, namely if this map is injective, then this sequence is exact here. That's very simple to see. If this map is injective, and I have something here that goes to 0 here. Okay? So what is this map? This map is composition with I. So if I have something in the kernel of F that when I map it to I by I go to 0, then that something was already 0 in B. And if this map was injective, this guy has to be 0. So this means that this sequence is exact here. And the same argument goes here. If this sequence is exact here, then this sequence is exact there as well. This last map is surjective. If this map is surjective, then this map is surjective. So that's easy to check. What is hard, it's very hard, is, and it's hard for different reasons, is that this works on any category. So everywhere I'm using choose, the whole construction here depended on choices. Grabbed an element C inside of this kernel. Pick a preimage inside of this object. Map G to that guy. Pick a preimage here. In the category of R modules, whose objects are modules, or the category of vector spaces, objects are vector spaces, they are sets, and I can talk about elements of those sets. So I can do these things. But in an arbitrary abelian category, I cannot do any of this, because I cannot talk about an element of an object. So the statement is that this theorem is true on an arbitrary abelian category. This is not trivial. We are not going to need it. I think we're only going to use our modules. But for those that do algebraic geometry, you do need this. And yeah, so the way to prove this is that essentially any abelian category can be realized as a full subcategory of a category whose objects are sets, or as a subcategory of a category that has a functor to sets, so you can think of the elements of an object for an arbitrary abelian category. And then you need to check that the existence that is guaranteed by this theorem does not depend on the embedding of your category into this other more concrete category. So that it ends up being a nightmare of set theory that I don't want to talk about, that I don't understand. So that's one way of doing it. Another way of doing it is trying to be abstract enough of doing this diagram chasing without choosing elements. And I ask you whether or not you can try it. So that's probably as hard as thinking on set theory. So try to do this argument without talking about this little element C inside of here that is not allowed for an arbitrary category. Okay, so it's not true that you can talk about an element of an object in an arbitrary category. So try to do this without using this symbol, belongs to. I do not know how to do that either, so that's why I'm not going to talk about this theorem. I don't think I'm going to use that theorem though. What else do I need to say about this particular theorem? I think that's, yeah, so those are the two techniques to try to prove this, that you can embed your category into a concrete category. That's not so hard. Or that you can avoid diagram chasing. All right, so with that theorem, we can prove something which is more useful, which is that theorem there. So proof of the theorem. Just grab that, just apply this lemma at each n. Okay, so we have, I think I switched from ABC to CDE. So I'm going to use CDE now for the theorem. What do we have? Well, I have C. Probably this is going to be too small. I have C. Let's say N to DN to EN. And this one is exact because I started with an exact sequence of complexes. So for each N, I have a short exact sequence in my category. In this case, R modules or whatever abelian category you chose. So this is exact. And I can apply D to that guy. So this is Cn minus 1. Differentials go in that direction. D, I get Dn minus 1. And this is the map that I started, and this one is also exact. D, En minus 1. And this diagram commutes because these were maps of complexes. So these diagrams commute, meaning these maps here are maps of complexes. Okay, the kernel in this arrow like this, probably Zn is a bad name. Let me call it Cn. So these are the, I think I've called them chains. Okay. So these are the guys that are in the kernel of G. This is in the kernel of the differential here, and this is in the kernel of the differential here. So these are the kernels of differentials by definition. Same diagram that I drew there. And since this guy commutes, then I have this guy here. And the same thing for the co-kernel. I can look at the co-kernel of the differential. What is the co-kernel is Cn minus 1 divided by the image of D. And the image of D were what I call the boundaries. So this is Bn minus 1. And this goes to 0. And I managed to run out of board again. So this is Dn minus 1 divide, oh shit. This Bn minus 1 is B of the complex C. So I should use a C there. And these are boundaries of the complex D. So this is Bdn minus 1. It goes to 0. And here I go to En minus 1 divided by the boundaries of this complex E. Okay, and then again, the map that goes from Cn minus 1 to Dn minus 1, which is this map here, is what goes back, well, sends boundaries to boundaries here, because I was in the map of complexes. And the map that goes from Dn minus 1 to En minus 1 sends boundaries to boundaries, so I have this map here. Moreover, the snake lemma says that I have a map from the kernel of G, which is this one. Well, first of all, no, not exactly. So I want to use this, and I want to claim that I have. I want to claim that I have a situation like this, and the situation like this needed. I can remove this. Not to confuse anyone, this is in a different color. This is an extra step of the snake lemma. The snake lemma started with something like this, that had two exact sequences of 4 terms, one ending in a 0 and the other one starting with a 0. So I want to find this in this picture here. Okay? So all right. Okay, so now I'm going to grab this row here. Oops, en minus 1. Pe n minus 1. And I'm going to apply the differential here. Well, the good thing about the boundaries is that the differential of a boundary is 0. So this d is well defined on this quotient. Okay? And d tends Cn minus 1 to Cn minus 2. Well, I guess it's that co-kernel, it doesn't matter. And this goes to Gn minus 2. And this goes to En minus 2. But the thing about the differential is also that the differential squares to 0. So d of this guy is 0. So the image is not in C, but it's actually in this chains. In the chains. And this very much looks like this row shifted by 2. So I have this like this. Moreover, this guy is also exact at this step. I claim that this guy is exact at this step and that this guy is exact at this step. Of course, since both arrows are exactly the same as the arrows that I have here, it's already enough to check that this guy is exact here and that this guy is exact here. Okay? And those two exactness I do get for free from the snake lemma. Because here, these two arrows here are exact at this point and at this point. So the snake lemma gives me for free this exactness at this point and this exactness at this point. So I've used already the snake lemma to claim that these two rows are exact. I'm not claiming any exactness here nor here. Now, with this exactness that I got already from the snake lemma, I can draw this diagram, and now I'm going to use the snake lemma again. And the snake lemma again is going to give me a map, therefore, from the kernel of this map to the co-kernel of this map. The co-kernel of this map, what it is? Okay. So the co-kernel of this map is, well, chains in Cn minus 2 modulo the image of D. So the co-kernel here is H Cn minus 2. Okay, so this is the co-kernel of D in this picture. And the kernel of this map, well, it's just the kernel of D here, and I'm already divided by boundaries. So this is H E n minus 1. So that's what I should put here in the kernel, H E n minus 1. And of course, I was stupid enough that I started here with n instead of putting an n plus 1, but it doesn't matter. You see, what the snake lemma gave us is a map from here to here, which is the connected morphism that we wanted. Okay? We wanted a map from the nth homology of the complex E to the n minus 1 homology of the complex C. That's what the lemma gave us. And the sequence is exact. So now I need to check what are the other two kernels that I have here. So the kernel of this D is, I'm going to write this, okay. So the kernel here of this D is the homology of the complex C in degree minus 1. The kernel of this map is the homology of the complex D in degree n minus 1. I have this map here and this map here. The snake lemma gave me this map here. The co-kernel here is HD n minus 2, and the co-kernel here is HE n minus 2, and this whole sequence is exact. And we just patch up with the next sequence by shifting the same diagram again by n, by 1. So that's the construction of the theorem. I think it doesn't make any sense to break here now for a while, so I'm going to stop earlier. Any questions about the proof of this theorem? We're only doing diagram chase. We haven't had any single idea. And but there was a claim that I made that this somehow gave me a functor, and which I don't want to state in terms of naturality and in terms of functors, but I want to at least make one concrete statement, which is I think I use C, D, E. These are complexes, and this is an exact sequence of complexes. And suppose that you have a morphism of exact sequences. So this would be C prime to D prime to E prime. So these are two different sequences that are both exact in complexes. And suppose you have morphisms like this, making this diagram commute. So every arrow there is a map of complexes. Okay? And for every n, that corresponding diagram commutes. And moreover, for every n and n minus 1, you're going to have an arrow commuting with the differentials. So that's the fact that these maps are maps of complexes. Suppose you have something like this. Then we have exact sequences from HCn, well, I guess it's Hn of C to Hn of D to Hn of E delta to Hn minus 1 of C and so forth. And this comes from E as well. And the same thing for the primed ones. Here we're going to have another delta. Here we have n minus 1 of C prime and so forth. And if I have a map of complexes from C to C prime, we've seen that we get a map of homologies. I don't know if we've seen, but this is absolutely trivial. A map of complexes induces a map of homologies between Hn of C and C prime. This map induces this guy. This map induces this guy. This map induces this guy. This map induces this guy, and so forth. The fact that this commutes is absolutely trivial. The fact that this commutes is absolutely trivial. The fact that this commutes is not entirely trivial. We constructed this guy by diagram chasing. We constructed this guy by diagram chasing. You need to check that this diagram commutes here. So that's the naturality of the construction of this delta. And this is certainly going to be in a homework, or it's going to be in a test if there's a test. So I'd rather you do it. So check that this diagram does commute here. All right, so that's the naturality of the delta. Okay, so let's talk about homotopies now. So I stopped. I think, and that's the last introductory part is going to be this. It's going to be chain homotopies. All right. How do I start with that? Okay, so better proof what I think I'm going to do what the book does, which is smart. A complex of vector spaces is trivial. There are no non-trivial complexes of vector spaces in the sense that a complex of vector spaces is always quasi-isomorphic to its homology. So if you have a complex of things, a complex is used to get invariants of objects. So invariants of modules or invariants of varieties or whatever it is, you put them, you get several objects, connect them by arrows, you get a complex, and you're interested in computing the homology of this complex. question. Does this guy remember the whole complex or not? Do I lose information by computing the homology of a complex, or do I keep the whole structure that the complex has? A complex looks like something complicated. I have objects and I have arrows between them, and the differential squares to 0. And these guys are subquotients, and I no longer have any arrows. You see, these are just groups. These are just vector spaces. So if you talk about a variety, the complex that computes the Rem homology looks much more complicated. It has the Rem differential than the Betti numbers of the variety, just as the dimension of the vector spaces of the cohomology of the variety. The question is, if I give you the Betti numbers of a variety, so that's the Rem cohomology of a compact manifold, do you know that the Rem complex? Do you understand the Rem complex? So that's an honest question. Do you have more information? Do you have the same information here and here, or you lose information? And well, at least let me state what does it mean to lose information, or in which sense I'm talking about losing information. And it's this. So I would say that two complexes, a morphism of complexes, F, a morphism of complexes, induces a morphism of homologies. So I would say that F is a quasi-isomorphism if it's an isomorphism. So for every n, the nth homology of C is isomorphic to the nth homology of D. But not only that those two modules, these are R modules or vector spaces or whatever the category you're working in, not only that these two are isomorphic, but the isomorphism is induced by this F, which is a given map of complexes. So that's what this F is, being a quasi-isomorphism. So if you have a complex of vector spaces, so let's say that your abelian category is K vector spaces, and you're given a complex in that category. So this is some Cn plus 1 to Cn minus 1, oops, to Cn. I said that I was going to use the arrows in the other direction. I think that's never going to happen, so I'm going to keep the arrows that way. Cn plus 1 to Cn minus 1. And I look at the homology. And I put the differentials to be 0. This is an honest complex. The square of 0 is 0. So this is a complex which is much simpler than this complex because it doesn't have any differentials. So what's the homology of this complex? Okay. What's the homology of this complex that is here? Can anyone tell me what the homology of that complex is? It's a complex with 0 differentials. So I can only guess two things. One of them is 0. Is that the right answer or not? So what's the right answer? Come on, I want to hear one guess. What's the homology of this complex where every differential is 0? Thank you. It's the complex itself. The kernel of this map is all of it because the map is 0 and the image is 0. So there's nothing to divide by. So in degree n, the homology of this complex is Hn of C. The homology of this complex, by definition, is that. So clearly the homology of this complex is isomorphic to the homology of this complex. Okay? Because the homology of this complex is this, and this is the homology of this complex. So what happens is that on the category of vector spaces, there are quasi-isomorphism between these two complexes. So this exists both in this direction or actually in this direction as well. So there exist morphisms of complexes that induce the quasi-isomorphism that we know it has to exist. The hard part is to prove that there is a morphism of complexes. Once that you have a morphism of complexes, it's going to be trivial to prove that it has to induce the identity isomorphism. This is true for the vector spaces, and it's not true for our modules. It's not true. So let's try to understand why. But the whole point is that if I am working in the category of vector spaces, then you might argue, well, why do I care about complexes of vector spaces if any complex of vector spaces is quasi-isomorphic to its homology? Then why do I care about having differentials if I can just replace any complex by its homology? And the homology is just a bunch of vector spaces in each degree. It's a graded vector space. It doesn't have any differentials. As soon as you move out from vector spaces to some other kind of categories, for example, vector bundles or R modules for a ring, you no longer have this result. You cannot replace a complex by its homology. And you should guess why is that. So let's do this for vector spaces. So Cn, inside of Cn, we have this differential d to Cn minus 1. And the kernel is this by definition. Okay? And the co-kernel is by definition Cn minus 1 divided by Bn minus 1. Okay? So this by definition is the co-kernel of this map D, and this by definition is the kernel of that map D. Okay, so this is a vector space, and this is a subvector space of Cn. So I can find a vector space P prime n that summed up with Zn is Cn. Actually, this is equal to Cn. This always exists. Whenever I have a subvector space of a vector space, I can find a complementary subspace. Okay, so what can I say about this Pn prime? And what can I say about this Zn? Okay, so let's recall what the definition of homology was. So the definition of homology in degree n was that Hn of C was a quotient of Zn divided by the image of D. And this was Zn divided by Bn. And the image of D, well, let me write it in a different way, as D of Cn plus 1, which by definition this guy is equal to this guy, to this Pn. So what I see from this is that we have this exact sequence now, from 0 to Bn to Zn to Hn. So that guy is a quotient. But then again, on vector spaces, any short exact sequence is split. This is a subvector space of this, so I can find a subvector space of Zn which is complementary to Bn. So this Zn itself is Bn, which is naturally a subvector space of Zn. By definition, is inside of here. But then I've chosen another vector space, H prime n, inside, that I know it always exists. And what I know is that this guy here is isomorphic to this. Right? Because the quotient of Zn modulo Bn is isomorphic to H prime n, and by definition is also isomorphic to the homology. So this guy here is isomorphic to Hn. Okay, so how about this now? Can anyone describe me this guy? the complement to chains inside of Cn. What I'm after is I'd like to construct a map from Cn to Cn plus 1. So I want to construct a natural map from Cn to Cn plus 1. We do have a map from Cn to Cn minus 1, which is the differential. What we have is this. This we want, we have. And what I want is this. For any n chain, I want to construct an n plus 1 chain. And I want to exploit the fact that I have explicitly the splittings in the category of vector spaces. So Cn plus 1 here comes with a map, which is D to Cn. But the map D does not land only in Cn. It lands in Bn, which is inside of Cn, which is this Bn here. That is inside of Zn, and this Zn is inside of Cn. So what I see is that Cn is split between a subvector space that is a homology, another subvector space which is the boundaries, and then another subvector space, and who can identify these boundaries? This guy here. Well, yeah, go ahead. Okay, so one guess here is that this B prime n should be in the image of D. So one guess here was that B prime n is the image of D, which is in Cn plus 1. I take D, it lands in Cn. And these, by definition, are the boundaries, Bn. Is that true? That can never be, because the image of D is inside of the chains. Okay. Oh, but let's look at this line here for Cn plus 1. This is equal to Zn plus 1 plus B prime n plus 1. What I said is that I want a map from Cn to this guy. And this is Zn plus B prime n. And I want a map here. I want someone to construct that map or to try to describe to me what is this B prime n. We have time, so. We can spend some time here. It's 42. I'll give you 3 minutes. So notice that, but at least I want to use something that Diego was thinking about. So I have this Cn, I have Cn plus 1. I have the kernel here to Cn minus 1. The kernel of this is D and this is D. The kernel of this map is Zn. And the rest of the kernel is B prime n. So B prime n is naturally isomorphic to Cn modulo Zn. It's a splitting of that quotient. What else can I do? What do you think? Actually, topologically, this map is kind of interesting too. But anyways. There aren't that many guesses to make. If I have an element in Cn, I want to get an element in Cn plus 1. And I'm claiming it exists, so there's no choice here. The first guess is going to have to be correct. So what are the splittings that we're forcing to have? We have a map from Zn to Cn. We do not have a map from Cn to Zn. The map that we have is the inclusion from Zn to Cn. Once I've chosen this B prime n, I have chosen a map in this direction. Because that's a projection. That's what splitting does. So from Cn, I can construct things in Zn. And I can construct things in this I can project to this other space if I want.
What do you use the analogy with the vector bundles like a section?
That's correct. This is exactly a section. So I want to hear that. I want to hear how can you construct an element in Cn plus 1? But that's correct. This is exactly a section of that map, of that inclusion. On the other hand, this guy, Bn, is the image of Cn plus 1 by D. And then this D sends Zn plus 1 to 0. So this Bn here, I can identify it again, so which is what I have there. I have this Cn plus 1 that maps by D to that guy Bn. This map is surjective by definition. And what's the kernel of that map? And by definition, that's the kernel of D. Okay? So now again, I can choose a splitting. And I can think of that Bn as a quotient of Cn plus 1 or I can choose a splitting of that. So now I start with Cn, an element in Cn. I'm going to take D, well, no, sorry. And I want to get an element in Cn plus 1. So how do I get an element of Cn plus 1 now? So now I have this map from Cn to Zn, which is here. And now I look at Zn, and I have a map from this Zn to this Bn, which is here. And now I look at Bn, and I use that splitting of that one. And I have a map like here. Because on vector spaces, I can always split a sequence. And I haven't made any choice, except the splittings. So I've chosen this subspace. This gave me a unique map from Cn to Zn, which is the projection. Now I look at Zn. Zn is the homology plus something else. And that something else is in the image of Cn plus 1. Okay? But there's a kernel. Choose a splitting. On vector spaces, you can always choose a complementary subspace. So once you choose a splitting, so once you describe Cn plus 1 as a sum of two things, as this Bn plus something else, well, plus some other space, I'm going to call it C prime if you wish, then you get a map from Bn to Cn plus 1, which is the inclusion the other way around. So this gave us a map from Cn to Cn plus 1. Let me call this map S. And let me make the unique claim that is important. Claim. I mean, there are many choices in what I've made, because there's all these splittings. But there's one thing that is independent of all the choices, and it's the fact that D is equal to DSD. So this S depends on a lot of things. However, this S maps things to kernels of differentials. So as soon as I apply D, that S essentially disappears. All the choices disappear. So this is a trivial check. The D is DSD. And this exists for vector spaces. So a complex C, a complex C, such that there exist maps. There exist maps Sn from Cn to Cn plus 1, satisfying D is equal to DSD, and I'm here. I need to choose the right. I need to choose the right subindexes for all of them, and I'm sure I'm going to do this wrong. So let's do the diagram. What I have is Cn. I can look at D to Cn minus 1. Or I can look S to Cn plus 1. Or I can look at D to Cn again. What I'm saying is that, and here I have Cn plus 1. And here I have D. So what I'm saying is that dsd is equal to D. Okay, so this is dn plus 1. This is dn. This is Sn. And this is dn plus 1. And this is dn plus 1. So here is n plus 1, n plus 1, n plus 1. Okay, so a complex such that this guys exists is called split. Why is it called split? Because S shit, I have 5 minutes, so let's do this. I'm going very, very slow. Should probably rush up a little bit. So this map S is going to give me a quasi-isomorphism between the complex and its homology. And a complex that is split and it's also exact is called split exact. So an acyclic complex and a cyclic complex that is split, is called split exact. Okay, so the way we've chosen our S, let me do this quickly. I'm going to give definitions. A map of complexes from C to D is called null homotopic. If there exists maps Sn from Cn to D. Shoot, no. This is not what I want. Sorry about this. What I want to do is this. I'm sorry. Let me do this. This is going too fast. Cn, C minus 1. I'm going to take this to Cn plus 1. This is going to be an S. So this is going to be from C to C. So here are going to be my S's. Here is going to be D. Here is going to be D. And I'm going to take an endomorphism of this complex. There's going to be a map of complexes. So this is Fn, and this is Fn minus 1, and this is Fn plus 1. And a map of complexes from C to C, an endomorphism of complexes, is called null homotopic if Fn is equal to Sd plus ds. In general, if you choose any maps, just any maps S from Cn to Cn plus 1. So these are called splittings, from Cn to Cn plus 1. Choose them arbitrarily. And you form this. I claim that this is a map of complexes. Let's stop at there. Let's do that, and let's stop there. So I claim that if you choose S arbitrarily, these guys here are a map of complexes. So of course, not every map of complexes is of that form. So those are the special ones that are called null homotopic. So for that, so let's define G to be SD plus DS. Of course, here there's an n that I should put in, but Gn is Dn composed with Sn minus 1 plus Sn composed with Dn plus 1. Okay? So this plus this is the definition of this vertical map in this picture. And let's look at D times G. Oh, by the way, yeah, so this S should be splittings like those. I'm going to require that this splitting satisfy this condition. Otherwise, it's not that it's arbitrary. So this S should be such that ds is equal to D. So let's look at dg. So this is dsd plus dds, which is dsd, and I look at gd, and this is sdd plus dsd, which is dsd again. So these two are equal, regardless of that condition there. If in addition, these two guys, if in addition these were split in the complex was split, then these two will be D. Okay, so but we see that these two guys are equal, regardless how we choose our S. So for whatever choice of maps S, we get chain complexes. So now I claim that those complexes are called non-homotopic because of the following. I'm going to take only 1 minute. We've seen that these are chain maps. I think I'm going to have to do this for so I'm gonna, okay, yeah, so I'm gonna, anyways, I'm gonna have to review it next time. So what I'll do next time is the following. I'm gonna take two different complexes, I'm gonna look at two different maps, and I'm gonna ask whether or not two different maps induce the same mapping homology. And for that, I'm gonna have to use this S, but going from, yeah, so mixing two different complexes. So I don't wanna repeat definitions now and write them, so I'll do this next week. But starting next week, most probably I'm going to go much faster.